Hello. So we are going to take notes on 53.1 and 53.2. So I'll do my famous, amazing cutting. Hey, actually, that was really good. This particular strip, I don't know how this works sometimes. It's just the way it is. But there's a lot of really important, testable information on here. So I'd pay really close attention and make sure that you feel comfortable and you understand what we're talking about, because every time I see this strip I can think of, I don't even know how many test questions that I've been on different tests. We haven't really even talked about tests. That's something I need to do and put on the resource page so you know what exams look like. All right, so we're going to start off with, whenever they say pattern, that's what you want to speak to. So you're wanting to see connections that you can explain, and it's explain how. So let's talk about what explain means first. There's really two parts to explain. When you explain something, I don't know, let's just pretend like that you're wanting something that your family's going to think is maybe not necessary and probably expensive. First thing you're going to have to do is make it really clear, like what you're talking about. So you're going to want to provide good information, details about exactly the what. And then the big difference between explain and describe is talking about characteristics and being able to almost close your eyes and see whatever it is in your head because you've been so detailed with what it's like with the characteristics. Explain is, what is this? And then why it's important. So just always go back to thinking about what you would have to do if you were trying to get something that was a little frivolous, maybe from your family. Okay, so explain how the pattern of dispersion, well, that's a vocabulary word. We do this when we have words. That's called, well, I made that up, but whatever. We call them buzzwords. So we put this squiggly line underneath it, which means that's a vocabulary word that I need to be able to understand. And they're saying, how does this pattern of dispersion is often determined by location and abundance of resources. So let's put another buzzword under resources. Do we know what resources are? Resources are something that they're needed. We'll just make it real simple, for life. So they're things that are needed for life. There's varying degrees of how needed they are, but still, there's something that has to be procured. Often they're competed over, but there's something that's needed. So let's talk about what this is. So first we need to say what dispersion is. So dispersion, you could also, it's also known as dispersal. It's just where items or organisms are located in space. So it's the spatial location of whatever you're talking about. So let's go back under here and put these so we know that those are important words. So let's reread it again. So tell me what this is and why it matters about the relationships within these spatial locations with the focus on the resources involved. So there's 3 patterns of recognizable patterns of dispersion. So let's just put that here. There's 3 patterns. The first one is random. So I'm going to make a little box and I'm going to draw what random looks like. So when we say spatial location, there's my space. And now let's locate, I don't know, organisms. Let's organize, like maybe, I don't know, different types of organisms. Doesn't really matter. So I'm just going to randomly put some locations there of the organism. So this is the organism, and this is random. So that's what it looks like. I'm going to move my notebook where I can see it. I hope I don't do something with there. Okay, that's good. Let's do 2. Let's do the second one, and we'll come back to looking at this pattern and then laying resources on top of it. So another one, another dispersal patterns, let's go ahead and put that, of dispersal, where things are located in space, would be clumped. So you might have, let's say, some organisms there and some here, but they're not all over the place in a random way. They're clumped. They're in very particular spots. There's a bunch of them here and a bunch of them here and not really any place else. So let's do the last one. This is the one that's like my favorite one to draw. I'll have to tell you what I saw before. So this is uniform. So the spacing is pretty regular for uniform. So now let's connect that to what different resources there might be in the area. So we'll go back to random. So if you think about random means it's not of any benefit to be here rather than here. So this would be, with random, you could have resources pretty much that are all over. That's one option. Or you could have almost no resources. Hey, I gotta move my head. So you either have resources that are everywhere and it just doesn't matter where you are. It's good here, good here, good here, good here, it just what doesn't matter. Or you could have poor resources that are everywhere. So all over in space. So it's just as bad to be here as it is to be here or here or here. So that's what random tends to mean, that there's no correlation with the location of resources. Versus clumped, this tends to be an indication that the resources are going to be located in just a few areas. So they're clumped here. So I think what I'm going to do is I'm going to take my highlighter and I'm going to let the resources be yellow. So in the random one, they're everywhere. In the clumped one, the organisms are where the resources are. Now, uniform is a little bit different. So even though this might be what you see, if you went out in the field, I don't mean like a field, I mean the field to study, and you noticed, hey, I see a cheetah here, a cheetah here, a cheetah here, and a cheetah here. And they're really as far away from each other as they can be. What you may not notice is that if you were a cheetah, you'd know, I know what my space is. So if I'm this cheetah, this right here is my space, and I don't go over here because that's this cheetah's. We fight at this border, and this border may change a little bit, but pretty much I can't have the whole thing. I can't manage the whole thing. So often uniform is an indicator of territoriality. What a word. So there's territories. And I went to a place called Fossil Ridge in Texas, and they had cheetahs, but they also had like all of these herd animals out there. Like they had, I think they had wildebeests and I don't even know what all they had, zebras, but the cheetahs had a pen that looked like this, and there was a cheetah at every corner. Every one of them had their own little spot that they guarded within the pen, and they all were looking at what they wanted to eat, but they couldn't eat. So uniform has to do with territoriality, because resources in nature are not uniform. So the other thing that nobody really talks about here, but if you see this dispersal pattern that's very uniform, usually the resources are man-made, because we tend to put things in a really predictable pattern. So man-made resources. So does that make sense? How does that work? You feel okay with that one? So you want to be sure that when you answer this question, that you don't just talk about the pattern, but you talk about the connection that there is to the resources. So when I explained the what was where it is in space, and the why it's important is because there's a correlation with resources that you can infer from going out and seeing organisms that are all clumped here and clumped here. I can infer that there's resources at that area and not so much every place else. Okay, so that's part one. So I'm going to come up here and put, that's question one. Question two, leading from this, one species of forest bird is highly territorial. Hello, uniform. While a second lives in flocks. Okay, so now we're going to predict what it would be like as far as if you walked out and you looked in an area and you were looking for the forest bird. So I'm sure you figured out that the forest bird would have a uniform dispersal. So now let me just say something about when you write. You don't get any extra consideration if you say, well, it could have maybe a uniform. You just need to say it, because you're either right or wrong. So go ahead and just make your statement. Don't hem and haw around and try to go, well, it's possible or whatever. Just say it. This is not English. We don't use a lot of words. So the forest bird, I'm just going to be strong with my statement, would have a uniform dispersal pattern. So I'm using the words that matter. This is the name of it. This is what the type of pattern is. So it would have a uniform dispersal pattern. And then I need to say because. So I need to say why. So because organisms that are territorial are going to space with the most distance between each other on their territory. And the other thing that you'd want to say is that they, by species, have a set amount of space as well. So this is where we're getting into a lot of the changes that a lot of the organisms are getting crowded. It's crazy, but there's bears that are taking over Asheville downtown because people aren't out because of COVID, and bears just got a bigger territory. So the competition, this is all about competition with humans in Asheville has gone down, and so the bears are just moving on. So that particular way of answering the part of the question would hit on providing enough information. What you don't want to do is say the bird would have uniform and then stop. You've got to have some legs on it. Like, it's got to have the support underneath it for your statement. So now we have birds that live in flocks. Flocks are naturally clumped. So I would put that. I would put flocks are naturally in a, and I'm going to use my words correctly. It's not just clumped, it's a clumped dispersal pattern. So they're naturally in clumped dispersal patterns. Most of the time, birds that are in flocks are social. They're also in flocks or herds for protection. So you would find these, organisms. They would travel together. So they'd be located together, so I could just remove that. And this is what you want to do when you're also writing for your test answers. Don't go crazy and spend time marking this out. If it's marked through, nobody can read it. Like, I'm not allowed to score it. So I liked the word located better. So they're going to find them located together, and it's going to often be in areas of shelter. So for protection, I'm going to put that in parentheses, or resources, water, food, light, shade, whatever that they need, something they need. So it's much more likely, if you had a test question, that these two would come together. And you would be asked this question with the explain built in. All right? So, learning real quickly that I can't do this on one page. 3, let's show you what else we do. When I tell you that something for sure has been on a test, will be on a test, we put a T there. And I told you that this is also something that's been on a test before. So survivorship curves. So as I'm going to look through these, first of all, it's just contrast. So this is the differences, which means I can write about how they're the same, but I bet there's no points in it when you look at the rubric because it didn't ask me to. So contrast the 3, so 3 is important, survivorship curves, and they're going to use that term with the understanding that you know what it means. So we'll put buzzword underneath it. So let's go over here to 3 and let's draw those. So organisms have different almost methodologies or ways that they come at what's that differential success. Differential success is that you live long enough and you have offspring. So there's different methods for that. So one way to picture it is to draw this curve. So we're going to draw a graph. And we're going to put relative age here. And I'm going to talk to you about when you draw graphs and the way you get full credit. If you don't do what I'm going to show you, then you don't get full credit. So we're going to plot relative age, and they said survivors. So we're going to do this against the number of survivors. So there's a couple of things about this that we need to address now. You have to have increments. So you can't go in here without values on your axis. So the reason why we use the word relative age, relative means you're comparing things among a group. So for example, if we did relative age between me, Mr. Godsey, and Mrs. Horner, I'm older than both of them because you're comparing me to 2 others. Now, I'm not old, so that would be not relative age. So that would be where that you're comparing me either to everybody or just giving me my own. But when you compare the items that you're looking at to one another, so this is how you get first place in a race. It's a relative position of how you finished compared to the other people who ran the mile. Okay, so relative is really, really important. So I'm going to put 2 under here because it lets us do some things that are helpful. So relative age, every single thing is born and it dies, right? So I don't have to put time down here and try to figure out how I'm going to plot the life cycle of a fly compared to an elephant because they have different survivorship curves. I'm going to start off just by adding my increments here. This is young, everything's born, and they're young, and then they get old. So I don't have to put numbers here because we're comparing these organisms to each other, and they all start off young and end up old. So number of survivors. You know, if you think about it, you sure couldn't plot real numbers on here because you're looking at things like squirrels and humans and nasty fruit flies and all kinds of different organisms, but they all have low survival rates or numbers of survival, which could be measured as a rate, and high. So don't make up numbers. This is perfectly fine for labeling your axis with units. Speaking of units, number of survivors, you wouldn't know this, but I'm telling you, this is actually a log. So they would have that there. All right, so I'm going to walk you through the different ways that organisms survive. And we learned that there's 3. So let's start off with survival pattern 1. So when you're young, this particular group, most of their young live. So this would be a high viability of your young. So they live for a long time. And now we're having some die off because you notice the survivor numbers dropping. And they live mostly until they die. Like they live till an old age. So an example, this is 1. So an example of survivorship 1 would be humans, elephants. They have that type of a pattern. They don't have many young. The young they have live as a rule. And they live for a long time until they die when they're old. That's what this curve means. So let's write ourselves a little note. It's that the young live at a high rate. So most live, and they live till they're old. And that's when they die. So let's contrast that to a 3. So 3, their strategy is not having few young that live for a long time and die. Their strategy is to have a bunch of young, so immediately, as soon as they're born, they survive, right? Because they're born. But immediately, most of them die. So you're going to get this horrific drop in the number of survivors. Most of the young die. The very few that make it live to old age. So this is 3. I'll put myself a little note here, is that your young, so I'm going to put most up here. Most young die, and very few live to be old. Then there's this kind of weird one. You have your young, they lived, they were born alive. That's all this dot right here means. And over time, there is every day the same likelihood that you're going to die. The young don't die at a faster rate than the old. So this is constant rate of change, right? So there's a constant ability to face life or death every day that's the same. So if you're young, like an example would be a squirrel, and you're a few months old, it's just as likely you're going to die as the squirrel that's 4 years old. So this is the young and the old have, yes, the same chance at survival. So it's not favoring one or the other. For 3, I didn't put that in there, but examples would be things like flies, mollusks. Those are things that throw numbers at it. So we can say a little bit more about these. I'm going to change my color. And put that in general they're going to have few offspring, so few young, and they care with a lot of care. Think about that for a human. You don't have 40 babies at one time and hope that they make it. You have 1 or 2, and there's a lot of care that goes in there. And they tend to live a long time. So if we go down here to 3, they have tons of babies. So they have extremely high numbers. And the reason is they're playing the lottery. I mean, they're hoping a few survive. So they have short lives, and there's not a whole lot of survivors in there. So squirrels are kind of a balance. They have more young than we do, but they have less care than we do. So they have just less care of the young. So they become independent quicker, and they have just a life that's not predictable. So not predictable length of life. Because every day is the same odds that you're going to die. That's not true for us. If you're an actuary and you do insurance, when organisms are young, humans, your life insurance is dirt cheap because your odds of dying are really low. Now, if you get out here to like in your 80s, your odds of dying are really high. So you're not going to have insurance very easily, which is the opposite for the flies. If there was a fly life insurance policy, then it would be horrifically expensive at the beginning because pretty much all flies die. And then it'd be super cheap because by the time you made it out to this point, it's a good probability you're going to live a little nice fly life. Okay, so are we good with that piece? We can't do this figure, so I'm going to mark it out, but we can explain the inverse relationship. So inverse meaning one thing goes up and one thing goes down, of winter survival rate of parents and brood size. So what they're wanting you to say here is that you get the relationship. It makes sense to you that if you have, first of all, I bet you don't know what brood is. Brood is the number of young. So if you have a large brood, you have a lot of young. So let's write the relationship. There's a high brood is going to have a relationship of creating a low winter survival rate. not just of the parents, but also of the young. So of both the parents and the young. So if you have birds and they have a big brood and they have a bunch of babies to feed, they're going to spend an awful lot of their own time and energy feeding those babies, which it's going to be scarce resources. So let's just write these things. So there's going to take a lot of energy and a lot of food to feed a lot of babies, right? And all of this is scarce. So you want to have the ability to think about, if this happened to be a short free response question or built into one, I can't say one smart thing. It's worth more than 1 point. So I want to say several smart things. And the way you do that is by letting the connections be made. So I answered the question first of all. Yes, there's an inverse relationship. The higher the brood, the less likely you're going to survive the winter. Then I get into let me think about what I can say about why that is. And I start adding these pieces because these are where the points come from. The answer is going to be a point, but you got to have the rest of the points to make it. All right, so let's do 5. Mice that can't find enough food or that experience other forms of stress will sometimes abandon their young. And this is the nice version. Explain how this behavior increases fitness. Okay, so this is very common in organisms. It's kind of hard to raise, for example, rabbits for food because rabbits are extremely sensitive to stress. And when a mom rabbit is stressed, she eats her babies. So this is the reason behind all of that. Let's just work through it in our head. What's more important in the scope of the world as far as survivability? The new babies or the existing parents? It's the parents. So let's think about this. The parents are going to be favored. And when we mean favored, we mean selected for survival. So let's write that. Selected for. How am I going to write that? That's going to look weird. Oh well. Selected for survival. And this is over the young. So the parents have already made it past a lot of the things that would be dangerous that the young still have to go through. And obviously, they're of reproductive age. The young aren't. So that's the big key. So don't make fun, but anything that's like a key thing to say, that's a skeleton key. Don't laugh, don't judge. The key thing to say is that reproductive age is the big deal. So the reproductive age organisms, those are the ones that are going to be able to do the 2 things, right? There's 2 things. Live long life, and have a lot of babies. They can do both. When you've got your young, the only thing they can do would be live a long life. They are not at reproductive age. So they can't have babies yet. So this is the way that works. And speaking of that, we're going to add something in down here that's not on your strip. Let me move this so we can see. Okay, so this is an add. You can look at a population based on what organisms are reproducing, what are too young, and what ones are too old. So there's a definition for that called effective population. Effect means that you can make an effect on the number in the population. So let's think about what that would be. So let's draw a little line here. We've got newbies, the young, your juveniles. We've got old codgers, And then in the middle, what you'll have is you'll have a group of organisms. If this right here is the whole population, and I've plotted them on a timeline of who's old and who's young and who's reproductive age. So this is the group. Where'd that go? Wow. Okay, never mind. Reproductive age. Okay, I'm going to quit writing if I can't do better than that. Reproductive age. The young can't affect the population because they can't have babies. The old can't affect the population size because they can't have babies. The only group that can affect the population size are the reproductive age. So the effective population are going to be your reproductive age organisms. That's going to be different than the entire population, which is down here. The whole population is going to have the young plus the reproductive age plus the old. So the whole population has every member, but out of the whole population, only a small group can actually affect the size. So the effective population is always smaller than the whole population. It is a subset of individuals within the population. It's the subset of reproductive age organisms. Okay? All right. I think that's it for that strip. That's a really important strip. So now let's do our one more thing. Definitely on a test. No joke. On a bunch of tests. I know for a fact, for a fact that effective population has been on the test before. Okay? So I'm going to move this little guy. Well, I don't know what I did. I dropped something. I'm going to move it into Edpuzzle.